robots and balance, two words that when mentioned at the same time to a regular person might not mean much because we as humans walk and see the act as normal. But to every engineer, hobbyist and student building robots, they know that making a robot balance itself and walk might bring some memories and maybe some PTSD, from control classes to mathematical modeling down to PID tuning, heavily dependent on how your experience was. But when a self-balancing or walking robot walks, it is plain ecstasy. This is SABR, my self-balancing robot, and in this video I'm not going to go over how to build SABR by telling you what to buy and to connect, but more importantly I'm going to show my journey and the process, which is more of a cautionary tale of how to and how not to build a self-balancing robot. You'll understand what I mean soon. You're probably thinking, how would I know? Well, this is SABR, but this is also SABR, and this is also SABR. See what I mean? I built a stepper motor version, servo motor version, and a regular geared DC motor version, all with different electrical setups, length variation, mass height variation, software changes, mechanical characteristics, and limitations. These are the results of a lot of experimentation using the core engineering principles, continuous iteration, and improvements. Here's the TLDR. I'm an engineer who graduated after 5 years in university. In my country, we have a theory-based curriculum that lacks current innovation or updates in the field of study. Now, this means that there's barely any hands-on projects and applications from the ground up that can be worth even mentioning. Not that a lot of things aren't taught, but things that are relevant aren't really taught, to be honest. I mean, in my 5th year of mechatronics engineering, we were using Lego Mindstorm set for robotics. That should be enough context. But as a result, I have been self-taught and funded in my journey of practical applications, and I decided to build a series of robots myself from scratch. Starting with the scientific principles in physics and math, then applying those principles by engineering the electronics, programs, and hardware for optimal performance while building. Not only for learning, but to create real products, which is the ultimate goal here at Legends. Let's start from the very beginning. Three months ago, I made a list of robots to build, and the first one on that list was a self-balancing robot. Why? Well, in order to delve into control theory and system modeling even more. Starting out, I did what anyone does first and started with the most important step, research. I delved into the physics of how self-balancing robots work because I already had some context about it, but I needed to clarify and make sure that my memory was not mistaken. A self-balancing robot can be represented in the system model like that of an inverted pendulum on a cart. This can be shown in a 2D diagram like this, with the cart having a mass M attached through a rod of length L to a pivot on the cart. The nature of the system is that of instability, where the pendulum would fall unless it is exactly centered along the vertical axis under a center of gravity. The angle theta is the difference between the position of the mass when it's balanced upright versus its position when it's unstable and falling, either left or right. Here's what the equation of motion looks like. I'll link below some research resources and materials for mathematical modeling and system equation, which can be solved using Lagrange, Laplace, and whatever, but we're not really going to go into that. The simple breakdown is that the mass M attached to the rod is stabilized by moving the cart forward and back to counter the angular acceleration as gravity acts on the mass, resulting in a torque due to it moving around the pivot. When the mass falls forward, the cart moves forward at an appropriate speed to counter the falling motion, and when the mass falls backward, the cart moves back to counter the said motion too. Here are the major considerations. The speed of the cart needed to balance the mass at the center point depends on the speed at which the mass falls. This can be changed by the length of the rod. Let's go into the physics a little bit more. The torque created seems like the only force at play, right? But there's something else that resists this falling torque: inertia. In this system, we have torque from gravity. Tau, representing torque, is equal to mgl sine theta, where m is mass, g is acceleration due to gravity, l is the distance from the wheel axle pivot to the robot center of gravity, and like I talked about, theta before is the displacement angle from where it's supposed to be vertically aligned to where it is. Using this formula, you can calculate the torque needed by your motors to balance your robot and then multiply it by at least 1.5 to 2 times to make sure that they are well above the minimum requirement that you would need. The angle theta is the angle from the balance point that your robot should be able to catch itself from when it falls to. It can be small or large, but the larger the better. At least it should be able to catch itself from a 30-degree displacement, either forward or back. While for the length L, you can use the length from the axle of the motors to even the ground to the top height of the robot you intend to build. This is obviously an estimate, but you would greatly overestimate your torque if you overestimate the amount of length, because torque scales with length. Let's continue. Apart from the torque from gravity, we also have moment of inertia, I, which is equal to ml square, mass times length square. Using rotational dynamics, tau is equal to IA, or alpha rather, where alpha is the angular acceleration. Solving this gives alpha is equal to acceleration due to gravity over length all times sine theta. Or alpha is equal to g over L sine theta. Now, for small angles, alpha is equal to g over L theta. Therefore, angular acceleration is proportional to the tilt angle and inversely proportional to the length. As the rod gets longer, angular acceleration decreases. A longer rod creates more torque, but its inertia increases even faster. Torque scales with length, where inertia scales with length squared, remember? So in the end, inertia wins. That results in longer inverted pendulums being harder to accelerate and falling slower. But at the same time, the longer the length of the rod, the more torque it takes to counter the force that the mass exerts as it falls, and vice versa. This is very, very important. And it's why it's much easier to balance a long wooden stick than a pencil, because you can react fast enough and with enough force to counter the falling motion to keep it upright. Now, in my demonstration, I don't exactly use like a long broom or a pencil, but you know what I mean. I just had like a big can around. Now, let's engineer a physical robot with knowledge of how the system works. Here's the deal. It's 4 a.m. and 97.3% of the people watching my videos aren't subscribed. Emotional damage. This video alone was born from 200 kilobytes of footage I had to go through because I refused to make this video with a failed result. I needed something that worked, or at least something approximating something that worked. So a self-balancing robot is not an oscillator or vibration system. I can't just pump out videos non-stop because it's a maker channel, and running this channel has given me even more respect for building and maker channels from other people, because building takes time, money and effort. If you enjoy what I do, I propose a deal. Watch the video, I've got my next project at the end, subscribe, leave a like and drop a comment on what you want improved in version 2 of this project, and I'll try my best to implement the comments with the most likes on bipedal SABR version 2. Jokes aside, I really appreciate all the support, and I plan on building even cooler stuff, showing you guys how it's actually engineered to work. Now, back to the video. Here is the closed loop control system of the self-balancing robot. The robot aims to be balanced, and to achieve that, it has an IMU, inertial measurement unit, to measure the pitch or roll angle theta based on the orientation as it falls. This angle is used to find the error by comparing the difference between the current angle of the robot versus the set point it's supposed to be at. The error is used in the PID, proportional, integral and derivative controller, which I have discussed about in a previous video where I built a line follower robot. Feel free to check that out. To summarize, PID control algorithms work like this. The output signal from the PID is converted to the appropriate signal for motor controller, from which the motors act and correct the angle. Now, there are other control algorithms that can be used, specifically LQR, which I wanted to use on this project but I decided to set aside, or even Cascaded PIDs, which is just a PID feeding another PID, which makes it more robust and allows us to control more than one parameter at once. But that's for another video. The IMU measures the current angle at a fixed sampling rate, and this process is repeated very rapidly. With a properly tuned controller, the error between the measured angle and the set point gets smaller and smaller over time until the system reaches the set point and maintains it. For a self-balancing robot, this needs to be done at around 200 Hz, i.e. 200 times a second. Now, with all my research done, I selected my components. For my IMU, I used the MPU 6050 3-axis accelerometer and gyroscope. There are other options, of course, but these were readily available and I plan to use sensor fusion on them, and I'll explain what that is soon. Next, the microcontroller. I selected an S32 dev module because it has a fast 240 MHz clock speed, Wi-Fi and Bluetooth built in for connectivity, along with a bunch of other pros, leaving lots of room for upgrades. On the topic of motors, let's go over the pros and cons of the different motors for this build. We have stepper motors, DC motors preferably geared, and servo motors, yes, even servo motors. Let me explain. Stepper motors offer high precision and move in steps, which when paired with the right driver can be made very smooth through microstepping. They have good torque characteristics but are ultimately harder to control, constantly drawing near full current, and tend to get quite warm or hot. This also affects drivers and can result in thermal shutdown. Subtle foreshadowing. DC motors, on the other hand, preferably geared, provide good torque and are easy to control with PWM. They are reasonably efficient. Well, I think you should avoid sport gearboxes as they are less efficient if I remember, but ultimately they are the go-to choices. Servos, on the other hand, are essentially just geared DC motors with position control. However, in this case, you will need a continuous rotation servo motor, meaning just a simple geared DC motor. Servos offer very high torque for their size, but the drawbacks are speed and cost. The really fast servos are so expensive that one could probably buy the base materials for my entire project with one of those. Despite all this talk, guess what? I already had one NEMA 17 stepper motor, and since a lot of people use them for their self-balancing robot builds, I threw all sense to the curb and picked the simpler option and bought a second NEMA 17 stepper motor. To accompany the NEMA 17 stepper motors, I got two stepper motor drivers, which were the TMC2208, a well-known really silent driver with stealth chop. One of the things about stepper motors is that they are power hungry, so I charged up the only proper LiPo battery that I could call reliable to use for this robot. Starting off, the first thing I needed to do successfully was to get pitch and roll angles, of which I would use one of them for the self-balancing process. To do this, I needed the accelerometer and gyroscope data from the MPU 6050 IMU. An accelerometer gives you acceleration in the X, Y, and Z axis, while a gyroscope on the other hand gives you rate of angular rotation in the X, Y, and Z axis, i.e. angular velocity. To obtain roll and pitch from an accelerometer, we must assume the accelerometer remains stationary, therefore only measuring acceleration due to gravity. Applying some math, we express the gravitational acceleration vector in a level frame with the Z-axis in the same direction as gravity. From this, you're able to derive a formula for getting roll and pitch. I'll link all the resources for this below. But there's the problem. Gyroscopes are great at tracking fast rotation, but over time they drift, and that error keeps building up. While accelerometers, on the other hand, are noisy, less precise, and they can't tell the difference between gravity and real movement, so even moving forward can look like tilting. Therefore, on their own, neither sensor is reliable, and to solve this, we bring in sensor fusion. Sensor fusion is the process of combining two different sensors with the aim of getting a better result by using one sensor to compensate for the weakness of another sensor and vice versa. In this case, we combine the short-term accuracy of the gyroscope with the long-term stability of the accelerometer, using filters like complementary filters or Kalman filters to cancel out each other's weakness and produce a stable, accurate angle. I tried out the complementary filter first, combining the gyro roll and accelerometer roll because it was much simpler. A complementary filter blends the sensors based on thrust, where your final angle is equal to alpha multiplied by the angle of the gyroscope plus 1 minus alpha multiplied by the angle of accelerometer. Alpha is a constant between 0 and 1 that determines how much you trust the gyro versus the accelerometer. Gyro is for short-term changes, accelerometer, long-term stability. For example, if alpha is equal to 0.98, trust the gyro by 98% and 2% of the accelerometer readings to correct drift. After that, I tried a 1D Kalman filter, which is way more complicated. A Kalman filter predicts and corrects using system dynamics and noise model. The core math relies on two phases. One is the prediction with state update, and the second is update with measurement correction. Here's the formula. You can see it. I'm not reading all of that. But to summarize, Kalman filters are very accurate and adapt to noise. To make sure I was using the best method, I did several tests and plotted the graph using serial oscilloscope. I have several hours of footage of me doing tests. With the first circuit done on a breadboard, the next thing I did was to add the stepper motor control using the TMC2208 motor drivers on the breadboard. I was able to write the code to get continuous rotation using the step pin by using delays in microseconds between steps. The problem with using this delay is that it has to be very precise and code needs to be non-blocking to have the timing correct. And this is hindered by the Kalman filter and the subsequent PID calculations which run at a set sampling rate. The loop also needs enough time to run all the calculations, and I have seen some hardware timer workarounds for this, but I took a reasonably easier route being multi-threading. To do this, I ran all my calculations and the core code of the robot on one core of the ESP32, while the microsecond delay timer was run on the second core to control the step pin. As usual, I experimented to fully understand the stepper motor control, writing code for continuous rotation, direction control, how to stop step skipping by implementing ramps, and how to implement an acceleration profile to reach higher speeds. Please note, for a stepper motor to reach higher speeds, unlike a regular DC motor, it needs to start slow and continuously accelerate to reach its max speed, as these motors have high precision but are limited by the fact it needs to take steps. These steps become much smoother by microstepping, using the driver's 1/8 or 1/16 selection. And if I remember correctly, the DRV882, can't remember the name, I'll put it up in the video. The DRV sensor goes down to 1/32 or 1/32 step, which allows it to make fractions of a step and making it much smoother. Once I was done experimenting, I combined it all together on a breadboard, added a buck converter to drop the battery voltage, and I did some sample PID implementations. With that done, I hand soldered the circuit board, which was such a hassle, and if you solder things, you know it's a love-hate relationship. But this time, things are different with the sponsor of today's video, PCBWay. More on them soon. Now, the next hurdle, designing the frame. I designed SABR version 1 to have these long angled legs and a really high length from the ground in order to get slower fall times. With that done, I started 3D printing in my 3D printing hell. And if you watched my last video, you'll understand why. I have power outages roughly every 30 minutes, 1 hour, 2 hours, and within like 3 hours, I can have power outages like 10 times, as there's no constant power supply in my area. One thing you'll notice are my DIY wheels. I modeled them to have grooves which allowed me to slide in rubber bands for better grip on the wheels, as I was too broke to make my own silicone wheels as I had spent all my money on new motors. I am once again going broke from the addiction to building things, so please subscribe. Eventually, I was able to roughly assemble the frame, motors, battery and electronics. And then the robot had its maiden balancing act. I tried to get the robot balancing, I really did. And if you notice, my wheels seem to perform just enough, but I wouldn't know that this would cause me more issues than I could ever expect. Let me tell you, this was torture. The motors kept skipping steps as the robot tried to balance itself, and I just didn't know exactly why. But after analyzing it, here were the core issues I could come up with. You know how I talked about calculating your torque? Yeah, I didn't do that. My instinct to experiment, be unconventional, and stress myself during the building process took over first. The robot didn't actually balance at a set point of 0 degrees because the weight wasn't evenly distributed, so it needed an offset which I later implemented. But most importantly, the robot had enough weight at a height from the ground where the torque needed to balance the robot was probably too high for the number 17 stepper motors, and the speeds I was actually trying to drive it out in order to catch up. I didn't have enough experience PID tuning, and that probably played a bigger role. And my wheels sucked. They had not enough traction, but that's something that I learned much later. Every time the robot attempted to stabilize itself, once it barely tilted, no matter the p-value I used, the robot just couldn't get itself to oscillate at least. Now looking back, I could have used a higher micro-stepping value for higher torque, but nonetheless, hey, it is what it is. Doing this caused me to push the drivers till they started having thermal shutdown, and I lost quite a couple due to this, where in testing the robot fell down and the buck converter got loose, and for some reason it would damage some things as I tried to brute force my way through this process. Very stupid, right? Here's the issue. You cannot out-tune hardware issues like this, because you would increase your KP, which increases the output of your motors to the point where they would move fast enough, but it would jitter. But if it lacks the torque and the speed to catch, the robot would never balance because it cannot catch itself. It cannot outpace the falling forces and all the things that it needs to outpace, torque and angular acceleration. The problem is even amplified further by using stepper motors because of their complexity of control. After doing my analysis, I went back to the drawing board and made this test platform for SABR with the aim of getting the most basic self-balancing robot done. None of the angular bipedal aesthetics for now. I 3D modeled it to be simple and 3D printed the parts. Of course, in like several goes with no power supply. Thank God for my UPS. Then I started building. With much shorter height of the robot and still with the same circuit board, I tried my luck again with a less unique design, and now it started to work, finally. But I was unsatisfied with the response, as once again, the robot just refused to balance properly and would drift off or fall. After roughly 3 weeks of inconsistently working on this project, I took some time off to work on other videos I posted late last year and put a pause on this project indefinitely. With more motivation and renewed energy, after succeeding at other things, I delved back in again. By this time, my first ever PCBs from PCBWay arrived.
Woo! Yeah, baby! That's what I've been waiting for. That's what it's all about. Woo!
Thank you to PCBWay for sponsoring this video and allowing me to get hands-on with designing a PCB that would actually be produced. As someone who has been designing circuits for years, but has never had the resources to get PCBs for my project, I can't say thank you enough to PCBWay. Within a few days, I picked up KeyCard for the first time in years, learned how to design PCBs once more again, when I'll link some of the tutorials below. I designed the circuit diagram with all the right connections, then moved to making the PCB, got the 3D model view, and I made the traces on the front and back copper layer. Added copper infill for 5V and ground for better signal integrity, and mostly used THT components as I still don't have an SMD setup to work with. Right inside KeyCard, you can get your designs ready for production with PCBWay straight up by using the PCBWay plugin, which I did. PCBWay isn't just a company that manufactures only PCBs like their name implies. And if you're like me and you want manufactured parts of exceptional quality, look no further than PCBWay for manufacturing your parts. They have a variety of manufacturing services ranging from CNC machining to 3D printing, sheet metal fabrication, and injection molding. You can go to their site linked in the description. Thank you to PCBWay for sponsoring the video and for getting me my first ever PCB design produced. I also got the Legends logo too. Now, I'll admit, I made some design errors. After trying to assemble my first PCB, I found these faults. The most detrimental one was that I made a copper fill and somehow shifted a trace between these two THT pin rows into the copper fill layer, which resulted in a short between the 5V and overall ground copper infill. I fixed this in the design, but physically I took a cutter and cut into the short point a bit to sever the connection, and this worked. This was the most dangerous and worst mistake. Secondly, I forgot to add a connection between enable and ground, which I fixed by adding a piece of wire between the two headers. My third error was a 0.8mm offset between the two mounting M3 holes by mistake. I don't even know how I made that mistake. And the last problem I faced was that I selected a footprint that was too small for the 2-pin terminals that I had by mistake. So instead, I simply soldered a GST connector with wires into it, and I should have made room for a switch to be placed, to be honest, but nonetheless, it works. And all the updated designs will be what you would get, not the ones with errors that I had to do all these fixes about. A lot of minor issues, but lessons definitely learned. After resolving all the issues, I assembled my first PCB and it worked. I completely revised the code and found out that it was clearly unoptimized, and I tried it again. But at the same time, with all the changes, I got the robot working close enough where it would oscillate quite a bit, but wouldn't just balance on my table. It would drift and fall, and no amount of increasing the proportional controller would fix that. Now, it was already 2026, the new year had arrived, and I was ready to put this project to rest, so I started my experimenting. Because these were failures that taught me a lot, I'll just briefly go over them and not dedicate a lot of time to them. I built 2 new self-balancing robots, and both failed for different reasons, but very important that you know, so that you can actually avoid them. I started with regular geared DC motors and a TB6612 FNG motor driver. The driver itself had issues and wouldn't run both channels properly, so I had to redesign around a single channel, which probably didn't supply enough current for the motors. The robot did try to balance, but it never succeeded. I swapped out the drivers and went with an L29810 motor driver, and still no success. I experimented with everything, including modular battery height, a modular design, different mass distribution, but nothing was able to make it work properly. The real problem turned out to be the motors. The DC motors needed a high starting torque, and any PWM value between about 0 to 40 out of 255 did nothing, meaning when the PID output was small, the motors simply wouldn't move. This created a dead zone where the robot would already be falling before the motors even responded. I tried fixing this by adding a feed forward, angle-based feed forward, and even different PID gains at different angles, meaning variable PID. But it didn't matter. Once the robot reached near balance, even if it was moving slowly, once it hit that dead zone, it couldn't make small corrective movements. After that, I got these 20 kg CM continuous servo motors from AliExpress. These were better, less slip, less backlash, and more consistent response. Now, I did this based on a video I saw, and they should have worked. But here's the catch. The servos used in those videos were high-end, really expensive Servos servos, and I only found out later after failing. They were much faster, like 10 times faster, and were about 8 to 10 times more expensive. I mean, they could have practically paid for this whole project, roughly 2 of them. Even with larger wheels to compensate, my servos were simply too slow for real-time balance control. So by this point, I had built 2 full robots, swapped motor drivers, tested multiple heights and modular designs, tried different motors, and while the servo-based version showed promise, motor speed and response time were far too little, being the most limiting factor. At this point, I was ready to wrap up the video and just post my failure and move on, but I locked in and gave it one more push. The upside? Those failures taught me a lot about motor dynamics, dead zones, and why actuator choice matters just as much as control theory, including learning to tune PIDs more and more on each failure. I was on the verge of giving up, and then by God's grace, I hit a stroke of inspired thoughts. I simply put it on my bed in frustration, and the robot started catching itself and balancing. It was friction. Friction was missing. I guess. The surface of my table didn't work with my DIY wheels, and then I noticed even my tiled floor didn't work either, because I didn't buy proper wheels, nor did I have silicone to make proper wheels. So I went to the carpet in the living room and boom, it started balancing too. Now I know people would say, oh, I'm taking the shortcut out, but given the circumstances that I don't have proper wheels on and I just have rubber bands that aren't even really thick enough, and they're also a lot of the time you could hear the PLA actually make contact with the floor, it makes sense that micro movements and micro jitters cause slipping when it's mostly balanced, because on the carpet that does not happen. But the story isn't done yet. I took more time tuning and tuning and tuning and tuning to the point this video got delayed by a week more until I got to this. But it still wasn't satisfactory, and not what I showed you earlier. Here is how the generic tuning process goes. Start by tuning your KP proportional controller until the robot can catch itself from falling and balance, but avoid having a KP that forces the robot to oscillate aggressively. Then tune the KD, focusing on dampening the response, but don't over-tune it, as this could cause more jittering. After your P and D are tuned, you can tune your eye controller to eliminate steady-state error and drifting. To be clear, I did this many times and still could not overcome the issues of jittering. So I went around trying different things. I saw a lot of things in the code of another guy who built a self-balancing robot and has been updating it for about 7 years. This man has been building and making better versions of his robot for so long that I had to take a look. Starting off, I tuned my P controller and found the most consistent range. I tried getting my D controller to smoothen movement, but it was too aggressive, above 0.7% of KP, which is lower than the recommended 1 to 2%. I found out from a lot of comments that most people who are control engineers love to stick to PI controllers, as the D-term in control engineering just exaggerates error and causes more oscillations when set in general, especially if they are based on error measurements. So a cascaded PI to P or PI to PI controller works, but the D-term is still useful depending on your robot. Many recommend that you use your D-term based on the measurements of your gyro, not the error calculated from the difference between the current and previous error. Next, I tried dynamic microstepping, and that seemed to let the robot balance closer to zero more easily, as it was using 1/16th step when moving less than 0.5 degrees away from the original set point, meaning if there was an error under 0.5 degrees, an absolute error, so negative 0.5 to positive 0.5, it would use 1/16th step, and other than that, it would use 1/8 step. Other than 10 degrees, it would use 1/4 step. But stepping from 1/8 to 1/4 or 1/4 step during balancing was a nightmare. It jittered a lot, made a lot of noise, and just didn't work. So I scrapped the whole idea and stuck with 1/8 step. Next, I tried Cascaded PID, where I used a position controller that counted the steps of the robot to serve as the input to the angular controller that corrected the robot. With an external encoder, this could be done using velocity or position to add another layer of correction. It did work, but I was still balancing heavy oscillations where the robot moved forward continuously as it balanced back and forth. Then also, the robot falling after some time too was also an issue. So I put it on the back burner. Then I tried a variable KP value based on different error angles to counter these. And nope, that did not fix things. After that, I went over my whole code and tried tuning my Kalman filter. I checked the ratio between my gyro thrust and accelerometer thrust, and it turned out to be about 75% gyro thrust to 25% accelerometer thrust. This made jitters and small movements produce much larger changes. I changed this ratio to over 95% dependency on the gyro, and the Kalman filter results were much smoother. And as a result, the robot itself became much smoother to control. And that is how I got to a version of SABR that actually works and balances itself. Here is more footage of the balancing robot. It's not perfect, of course. I stuck with just angular controller and did not implement the final position controller, as I was understandably tired of working on this and needed to do something else desperately. The swaying is caused by the robot trying to reach the perfect vertical alignment, but missing as the motors move either a little bit slower or faster than commanded. This requires a position or velocity controller to correct so the system can be very stable and position itself directly under its center of gravity. If there is anything I want to take away from this project, it is that failure does not mean something is impossible. It's just a learning curve, and I learned a lot through all my trials and error. And when you fall, you've just learned that your actions didn't give the expected results. Pivot, make gradual changes, and see things improve instead of outright giving up. This project really goes over engineering fundamentals, control theory, and the difference between theory and application. If you watched this far, I really appreciate you, honestly. Please consider liking, subscribing, and commenting if this video was useful to you and provided some form of information or entertainment. I'm open to seeing the advice from the comments from better experts on where I went wrong and what could actually be improved. Make sure to turn on post notifications too so you can see my shorts and other content. All the design files, including the updated and corrected PCB files, 3D model, list of components, and an assembly guide will be available in the GitHub repo. I will try my best to make the README as robust as possible. Also look forward to my attempt at a bipedal version of this robot, and with that, I'll see you in the next video. I'm looking forward to your comments to see what it would actually tell me to implement in the next version. See you next time.